Welcome back to The Explainer. Today we're unpacking one of the absolute most infamous and honestly fascinating moments in all of spaceflight history. Imagine for a second building a magnificent machine, a true technological marvel of its era, only to have it completely obliterated by a single microscopic typo. Well, that's exactly what happened with Mariner 1. We're going to break down the anatomy of this massive failure step by step just to understand how the absolute tiniest of human errors brought a towering rocket to its knees.
$554 million. That was the staggering approximate cost of the American Mariner space program, which covered missions 1 through 10. I mean, we are talking about an immense investment of money, time, and brilliant human intellect, all designed to explore our solar system. And yet, for the very first mission of this incredibly expensive program, this massive financial and scientific investment was put in complete jeopardy by an error so small you could barely even see it on a piece of paper.
All right, moving to Part 1, the race to Venus. Let's look at the intense space race pressures of 1962.
Okay, let's dive into this. Because to really understand how a typo like this slips through the cracks, you've got to put yourself in the environment these engineers were working in. The year is 1962. The space race between the United States and the Soviet Union is at an absolute fever pitch. The Soviets had already made multiple attempts to fly by Venus in the early 60s, and NASA was under this immense, crushing pressure to keep up and score victory. So, Mariner 1 was highly complex for its time. Look at the stats here. It had a mass of 447 pounds, aimed for a Venus flyby, and carried a modest suite of scientific instruments to measure things like cosmic dust and solar plasma. It was sitting on top of an Atlas Agena B launch vehicle, and the spacecraft itself made up of 54,000 individual components. But here's the really critical detail. Because of the intense pressure to beat the Soviets, the spacecraft was actually pretty hastily built. NASA engineers had been working on this brand new design specifically for Mars and Venus, but it just wasn't ready. So, to meet their deadline, they actually ended up using parts from the Ranger spacecraft for Mariner 1.
Which brings us to Part 2, 294.5 seconds to destruction.
So all of that preparation, all 54,000 of those components, and all of that intense pressure culminated on the morning of July 22, 1962. Let's step into the control room at Cape Canaveral. The excitement of launch is about to turn into a terrifying ticking clock nightmare. Let's trace this timeline together. T-minus 0 seconds. Liftoff. The Atlas rocket clears the pad at Cape Canaveral, and everything seems totally fine. But then, at T plus 150 seconds, the vehicle begins this unscheduled yaw-lift maneuver. Suddenly, steering is impossible. The rocket is flat out ignoring guidance commands. The clock is ticking down to T plus 288.5 seconds. Now this is crucial because this is just 6 seconds before the spacecraft is supposed to separate from the booster. And if it separates, it can no longer be destroyed. Finally, at T plus 294.5 seconds, the fateful decision is made by the range safety officer.
Veering off course, those 3 words are a launch director's absolute worst nightmare. The faulty application of guidance commands meant that the Atlas rocket was no longer flying toward space. It was completely, terrifyingly out of control. And the horrific stakes of the moment became immediately clear to everyone in that room. A massive, fuel-heavy rocket flying out of control isn't just a lost science mission, right? It's a deadly hazard. The vehicle was actively directing itself toward a crash, potentially right into the North Atlantic shipping lanes, or even worse, into an inhabited area. The range safety officer had literally seconds to act to prevent a potential catastrophe back on Earth.
Destruct command sent. At 294.5 seconds into the flight, they pushed the button. The spacecraft and the booster were intentionally destroyed high in the sky just for safety. And in an instant, 54,000 components and years of highly pressured work were vaporized into a cloud of debris.
Now, let's transition into Part 3, the hardware glitch. It's time to do a little autopsy on this failure.
You see, whenever a rocket is lost, engineers painstakingly review exactly what went wrong. It's like a giant puzzle. And the destruction of Mariner 1 actually started with a physical hardware failure. Let's carefully break down this cascading glitch, step by step. First, the Atlas airborne beacon equipment operated improperly. This caused it to drop out, which led to multiple periods without a rate signal. Second, because that beacon wasn't working, the ground receiver started sweeping. It was desperately trying to find the vehicle's beacon signal. And third, the system's computer accepted this sweep frequency, combined it with the tracking data sent to the guidance computation, and just started processing it. Basically, the system was flying completely blind and was forced to rely on a backup program to interpret all this messy data.
And that brings us to Part 4, the
the fatal missing overbar.
Because here is the ultimate twist of this whole explainer. The hardware glitch alone did not destroy Mariner 1. Actually, hardware fails all the time in aerospace, which is exactly why backup systems are coded into the computers in the first place. The real killer here was the backup code itself. Now, we need to bust a massive historical myth right here. A super popular myth, often repeated in tech circles and on engineering blogs, is that a missing hyphen in the code crashed the spacecraft. But if we look at the official NASA historical fact, the true culprit was an omitted overbar on the radius symbol, or R.
So the crucial point is, exactly how did this single tiny line over a letter cause so much absolute chaos? Well, the overbar is a mathematical notation used in the data editing program's guidance equation. Because the programmer missed this tiny overbar when transcribing the equation into the computer code, the program was allowed to transmit incorrect guidance signals. When the hardware beacon failed, like we talked about, this flawed backup code took over. It caused the computer to violently overreact to the sweep frequency. It initiated completely unnecessary course corrections, feeding totally incorrect steering commands to the rocket until, well, it had to be destroyed.
So, let's wrap this up with Part 5, the expensive lesson. Why software matters.
It was an incredibly expensive lesson for NASA, proving that out there in the vacuum of space, your software is just as critical and just as deadly as your hardware. But the story of the Mariner program doesn't end in destruction. And this brilliantly illustrates the sheer resilience of the NASA engineering team. They didn't just sit around and dwell on the failure. They immediately dug into the data, they identified that missing overbar, and they fixed the typo. They took the backup spacecraft, Mariner 2, and launched it successfully on August 27, 1962. That is barely a month after Mariner 1 exploded. And by December 14 of that same year, Mariner 2 made history by completing the very first successful robotic remote encounter with another planet. It returned absolutely vital information about Venus's atmosphere, mass, and magnetic field.
Which brings us to our final thought. The Mariner 1 disaster happened back in 1962 with early, primitive computer systems. But today, our lives are entirely dependent on software with millions of lines of code. Everything from our cars to our banking systems to our power grids. So if a single omitted overbar could vaporize a $554 million program in 54,000 components, it really makes you wonder, doesn't it? Just how vulnerable are the massively complex digital systems we rely on every single day? It's a fascinating reminder that in engineering, the absolute smallest details can have the most explosive consequences. Thanks so much for joining me on this explainer, and keep asking questions.